Epoxides are synthetically useful compounds, allowing access to many products. Epoxide can be prepared from an alkene in two synthetic steps by first forming a halohydrin, then treating the halohydrin with base to deprotonate the alcohol group, and cyclize. Epoxides can also be prepared in a single step from alkenes in high yield by using a peracid such as metachlorobenzoic acid, often abbreviated as MCPBA. Peracids have a peroxy group attached to the C-double bond O carbon. The byproduct of the reaction to form the epoxide is a carboxylic acid. This method for preparing epoxides offers several advantages over the halohydrin method. Performing the reaction in a single step decreases any losses associated with isolation of the intermediate halohydrin. The reaction is conducted under relatively mild conditions in comparison to the strongly basic conditions required to convert a halohydrin into an epoxide. The reaction is stereospecific. Trans-2-butene is converted into the racemic trans-epoxides on treatment with MCPBA. In the mechanism for this reaction, an oxygen atom is added across the pi bond to generate the epoxide. Note that there is a hydrogen bond between the peroxyhydrogen and the carbonyl oxygen in the transition state for this reaction, which facilitates the transfer of a proton to the carbonyl oxygen to form the acid byproduct. Hydroboration-oxidation is the third method for adding water across a nonpolar pi bond. This method is complementary to acid-catalyzed hydration and oxymercuration reduction. The method consists of two synthetic steps. In the first step, borane adds across the pi bond to form an intermediate, which is then oxidized with hydrogen peroxide and base to form the product alcohol. Below are two examples of hydroboration-oxidation reactions that illustrate two of the key features of this synthetic method. First, addition across a pi bond proceeds in anti-Markovnikov fashion, with the hydrogen adding to the most substituted carbon in the alkene. Second, the addition of the hydrogen and hydroxyl groups occur in syn fashion, whereas most of the other additions we have seen in this chapter occur with anti-stereochemistry. It is also worth noting that both these reactions proceed in high yield. Boron compounds are typically strong Lewis acids, as the central boron atom lacks a full octet. Because of its high Lewis acidity, borane itself cannot be isolated. Instead, the pure compound exists as the dimer diborane, with two hydrogens forming partial bonds with two boron atoms in a bridging complex. Borane also forms complexes with ethers like tetrahydrofuran. The oxygen atom in the ether forms a weak bond to the boron atom, providing some stabilization. Because of borane's strong Lewis acidity, on reaction with a pi bond, most of the electron density will go to the boron atom. The transition state for the addition is a four-membered complex, with the bond between the boron and one carbon atom mostly formed, while the bond between the second carbon atom and the hydrogen is more weakly formed. Since most of the electron density of the pi bond has gone to form the carbon-boron bond, the second carbon atom of the alkene develops a partial positive charge. This partial positive charge is preferentially formed at the most substituted carbon atom. As a result, the hydrogen adds to the most substituted carbon. Also, because the boron and hydrogen add at the same time, they add in syn fashion. This concerted addition of both boron and hydrogen avoids the formation of an unstable intermediate carbocation and allows the reaction to proceed stereospecifically. The anti-Markovnikov regioselectivity of the addition is also driven by steric factors. The boron atom, with its two hydrogen substituents, is more bulky than a hydrogen atom, and so there will be a greater steric repulsion with the more substituted carbon of the pi bond, inhibiting Markovnikov addition. The product of the addition of borane to an alkene is an alkyl borane. This compound has additional boron-hydrogen bonds and can react with more molecules of the alkene to form dialkyl and then trialkyl boranes. Once all the boron-hydrogen bonds have been replaced with boron-carbon bonds, the trialkyl borane intermediate can then be reacted with basic hydrogen peroxide to generate 3 molecules of alcohol and a borate anion. The mechanism for the conversion of the trialkyl borane to the alcohol involves coordination of the peroxide anion with the trialkyl borane. One of the alkyl groups then migrates from the boron to the oxygen to form a borate ester. It is important to note that this migration occurs with retention of configuration at the migrating carbon atom. The net result is that the syn orientation is maintained between the hydrogen and the oxygen. The process is repeated until all 3 alkyl groups have migrated from boron to oxygen. Then each alkoxy group is replaced with a hydroxyl and is then protonated to form the product alcohol. Hydroboration-oxidation of alkynes with borane is not a synthetically useful reaction. The addition of borane to an alkyne leads to the formation of an alkene, which can react further with another borane molecule to give a complex mixture of products. Synthetic chemists avoid this problem by using a pre-prepared bulky diborane, typically diamyl borane, which will add to only 1 molecule of alkyne. The reaction of a terminal alkyne with diamyl borane, followed by reaction with basic hydrogen peroxide, leads to the synthesis of an aldehyde via the enol. Aldehydes are fairly reactive carbonyl compounds, and this relatively mild synthetic method can generate them in high yields. Compare this method with acid-catalyzed hydration or oxymercuration of alkynes, which lead to ketones. The methods are synthetically complementary. In summary, the reactions in this chapter focused on the additions of non-proton electrophilic atoms to pi bonds. If the electrophilic atom possesses a lone pair of electrons, these additions typically proceed through a 3-membered cyclic transition state, avoiding the formation of relatively unstable carbocations. One example of this type of addition is the addition of carbenes with alkenes to produce cyclopropyl rings. Carbenes are highly reactive species, and typically must be generated in situ from precursor compounds. Bromine and chlorine add to alkenes to form vicinal dihalides when the reaction takes place in a non-nucleophilic solvent such as carbon tetrachloride or dichloromethane. If the reaction is run in water, the solvent will efficiently compete with halide anion to cleave the intermediate cation and form a halohydrin. Oxymercuration reduction is a synthetic method to hydrate alkenes via Markovnikov addition without going through a carbocation intermediate. This eliminates the possibility of rearrangement. Treating an alkene with a peracid, such as MCPBA, allows for the stereospecific synthesis of an epoxide under mild conditions. Hydroboration-oxidation is a synthetic method that allows anti-Markovnikov hydration of alkenes. The hydrogen and hydroxyl groups stereospecifically add in syn manner to the alkene. Alkynes can also be hydroborated using a hindered dialkyl borane. Oxidation of the product leads to the formation of a ketone if the starting material is an internal alkyne. External alkynes are converted to aldehydes using this method.